Earth is part of space. Check out The Center of the Universe and Carl Sagan's rather poignant way of saying the same thing at the link in the overlay cards and in the description. Hi, my name is Alex. I've argued enough for a lifetime. And this is audio science. Its visual content is quite limited, though not entirely absent. We're on YouTube after all. Still, put your headphones on, sit back, relax, and enjoy your commute or whatever else you're really doing right now. In addition, please subscribe and share. Doing so will help this channel a lot. Onto the Earth's atmosphere. What do you know about it? Think about it for a second before I start. What do you know about the Earth's atmosphere? What I want to do now is to show you the whole of the atmosphere, perhaps with a slight tendency to see things from the polar regions, because I live there, how it affects our environment and how fundamental it is for us. It is our environment, where energy, which is the basis for everything, moves around, but is never produced. How do we affect it, and how does it affect us? Depending on who you are, where you live, and by which means you get through the day, the answer to these questions will be different. I can't answer for you, really, but I can attempt to set the table and make you understand enough about the Earth's atmosphere for you to answer the questions yourself. Sit back, relax, and listen. Let's go. We divide the atmosphere into 4 layers usually, and of course, being the humans we are, we don't really do a good job of it. If you categorize, you need something to categorize by. We can use the temperature gradient with respect to altitude, height that is. In this way, and looking up, we get the troposphere, the stratosphere, the mesosphere, the thermosphere, and the exosphere. In the troposphere, the lowest layer, we find the temperature to decrease the higher we come up. This is intuitive to us because it meshes with our experience when walking up a mountain, for example. In the stratosphere, the air becomes warmer the higher we go. Now, warm is a relative term, of course. We're still talking dozens of minus degrees Celsius here, but you get the drift. We rise, and the temperature does too. On top of the stratosphere, we have the mesosphere. Here, the temperature drops again with height, while at the edge of space in the so-called thermosphere, the temperature rises the further we get out. There's also the exosphere with a more constant temperature profile, but well, you'll see later on. What about the ionosphere? If you've ever read anything about aurora or radio communication, you may have heard that expression. What is the ionosphere? Well, if we forget the temperature gradient but look rather at the electrification of the atmosphere, that is, how much electricity, electrons and ions we find, then we can define an ionosphere in some ways as the place where there is a lot of electricity. If that sounds a little vague to you, then that's because it is. The atmosphere is electrified, period. Just more so higher up. Then again, we all have some sort of inkling as to what is meant. Northern lights happen in the ionosphere, for example. That means they happen high up. What more do you need to know, really, standing there under it attempting to take pictures? It's good enough. We know the chemistry in the atmosphere quite well as well. It's 78% nitrogen, 21 and some % oxygen, the rest is more or less noble gases and stuff we put into the air like methane and CO2. These percentages may deviate from the average at any one given height because, well, they're averages. Now, for the pressure, you probably know that it decreases with altitude. At least it's supposed to. It does so too, in as perfect an exponential function as nature may allow. This is good. Because when we measure and see that it isn't at a particular height above us, we can investigate. Something's up. We're scientists. We love when something's up. So let's zoom in. Let's dive into that lowest layer, the troposphere. Tropos is Greek and means change. And things do change in the troposphere. We call these changes weather in the short term and climate in the long term. What fuels all these changes and makes it so difficult for us to predict anything? The Earth itself. You've probably heard about the physical process too, the greenhouse effect. The Earth is warm. Whatever's warm radiates infrared light. The closer you are to that radiator, as it were, the hotter it is. The troposphere then becomes the part of the atmosphere where infrared radiation, emitted by Earth herself, dominates all physical processes. Getting higher up means simply to move away from the radiator. Over the polar regions, the troposphere will be around 6 to 9 kilometers high. Over the tropics, perhaps 16 to 18 kilometers. It'll be your homework to figure out why there is such an altitude difference between the tropics and the polar regions. Here, we'll just look at the surface. The Earth's a rocket, you know? Just kidding. Only, I'm not really kidding. When a rocket cuts through the air, its surface gets hot too. Hot surfaces radiate a lot of energy. That energy moves things around. Close to it, there's turbulence. Depending on the speed, geometry and surface specifics of the rocket, you will have to get away from it by either a few centimeters or a few meters before there is no more turbulent flow, as it's called, and laminar flow takes over. Both Earth and rocket surface generate infrared radiation, which gets absorbed by the surrounding air until it is spent as you move away from that surface. I'm decidedly not kidding now, to be sure. We could therefore call the layers of turbulent and laminar flow on the surface of the rocket its tropo cone or something. We don't. It doesn't make sense. It's called the boundary layer. And we concede that the Earth has one of those too. The planetary boundary layer, the lowest part of the troposphere. We can usually see it quite easily because turbulent layers have a tendency to take everything that's in the gas and spread it out evenly over the whole volume. If you live in a city with a TV tower and you've been up on it at night, you may have seen it. There's going to be a volume of milky light over the city and darkness above. That's smog particles being distributed evenly over the whole volume of turbulence. Above that, there's laminar flow and you can't see the smog anymore. It's quite intriguing just how defined that borderline really is when you look at it. The border between turbulence and laminar flow, that is. And yes, the planetary boundary layer is larger in the tropics than in, say, Central Europe. If you've done your homework just a minute ago, then you know too why that is the case. Here's an interesting tidbit. Clouds can't exist within the turbulent layer. The cloud droplets would be distributed evenly over the whole layer too. There's fog, of course. But when fog happens, the planetary boundary layer isn't strong and only slowly distributes the particles the way I described it. Speaking of clouds, clouds consist of either such water droplets or ice crystals. Size-wise, these are neither macroscopic nor microscopic objects. In terms of doing physics with them, that means that we can use flow dynamics equations on them, but should only do so very carefully. It also means that we can use quantum physics, but that be about as impractical as it gets. The truth of how we deal with cloud droplets and crystals is close to how they built churches in medieval times. We've done experiments, saw what works under what circumstances, and ran with the resulting mathematics there and then. The other thing is that the droplets don't just appear out of thin air. They grow. Two molecules finding each other, catching a third, then a fourth, and so forth. Why would they find each other? The key word here is nucleation. If you want to get some extra knots in your brain, please read about it or talk to somebody who does research on it. Because it's complicated and I don't do complicated on this channel. The only thing I want you to take away is this little secret. Cloud physics is one of the most difficult fields in science. Forget those grey rainy things in the sky. Physics-wise, they're about as intriguing and awesome as it gets. I've been accused of loving them too. I do so for that very reason. And for another reason or two. Here, what about atmospheric pressure waves, for example? Technically, a wave is a series of oscillations that interact with each other in some way. So a pressure wave is a couple of oscillations in pressure being well coupled to each other. In our atmosphere, air pressure oscillates and waves build. The coupling happens through the molecules in the air. Now, of course, that was a little abstract. How would this look like in practical terms? Enter mountains. Yes, mountains. The wind hits the mountainside and gets pushed up. The weight of the whole atmosphere above pushes back. You'll find that the wind will be rather strong on top of the mountain. Nature takes the energy for the air accelerating in this way out of the pressure. So the pressure decreases and with it the temperature. If the temperature decreases enough, then clouds can build up. If you've ever seen a lentil-shaped thingy sitting there on a summit, then that is what happens. Lentil clouds are awesome. If you point a camera at them and run a time-lapse, you'll find that the air flows through the cloud. At least it'll look like it. Water droplets can nucleate for a while and then disappear again when they have left the mountaintop. When the wind reaches the lee side of the mountain, the pressure increases, the cloud dissipates, and that's all that's needed. Low pressure over the mountain, high pressure on the lee side. Air moving through both areas, but also vertically adhering to Archimedes' idea of updraft. Two oscillations, they're coupled through the airstream itself. Wave. The thing is though that there doesn't have to be a mountain in the way, and there won't always be visible structures in the sky either. If something stands in the way of an airflow, then there'll usually be some form of oscillation in the wake of it. Knowing that everything in the atmosphere is connected to everything else, that basically means that there are always atmospheric pressure waves. On top of that, there's other modes of wave generation which have nothing to do with anything standing in the way of anything else. Imaginary forces can do it too. Have you, for example, ever heard of the jet streams? These are top of the troposphere airstreams flowing from west to east. They're high up enough to feel the Coriolis force rather strongly. As they gain velocity, they may start to meander, moving the air around in large patches while doing so. At the end, you may find large volumes of low pressure alternating with large volumes of high pressure along the stream. High pressure, low pressure, coupled of course, since this is air. That's a pressure wave with a couple of 100 kilometers in wavelength. They're called Rossby waves or planetary waves, the largest atmospheric pressure waves we know of. In other words, there's a lot of energy in the Earth's atmosphere. I mean, that is what we talk about here, energy. Solar energy being absorbed by either the Earth itself or one of the constituents of the atmosphere. Ozone famously absorbs UV light on the way in already. Water vapor and methane notoriously absorb infrared radiation on the way out. Truth is, we don't completely know what's in the atmosphere. We use cover words like aerosol to hide that fact. Anything that's small enough to float on its own accord is called aerosol, basically. It's not quite right, but right enough for our purposes. Cloud droplets are aerosols. Smog is an aerosol too, and don't be too harsh on this seeming a cop-out. It's much more important to know what happens than to know every chemical to a fraction of a per mil. We call the overarching knowledge the energy budget, and we have good ways of measuring it. Take for example what's called the albedo. As of today, it is defined on Wikipedia as the measure of the diffuse reflection of solar radiation out of the total solar radiation on a scale from 0 to 1, corresponding to a black body that absorbs all incident radiation. Here is much as I can tell you what that means. It means that in the energy budget mentioned, there are losses. Energy leaves Earth. We should be glad for that too, since we'd slowly be fried alive if not. Energy leaving Earth can take many forms, and the albedo refers to a particular part of the radiation which may leave Earth. Go and check out maps of the albedo for, well, Earth. There are going to be surprises in store for you. Why, for example, is the albedo high in Northern Europe and Canada? That was homework, if you didn't catch my drift. By the way, did you know that according to some economists, smog may just be the solution to global warming? And they may just be right too. See, the greenhouse effect is what causes global warming, right? That is, solar energy is absorbed by the Earth itself, which warms up such that it sends out infrared radiation, which is then absorbed by greenhouse gases in the Earth's atmosphere and makes everything hot. But aha, I say, when we say smog, we often describe aerosols which contain chemicals such as nitric oxides. Nitric oxides absorb solar energy on the way in. That means the Earth isn't going to absorb so much energy and thus won't radiate so much, thus not warming the atmosphere so much. You know, when I meet somebody who has grown up in what can be described as a cult, it's difficult for me to be arrogant about that person believing in a flat Earth, for example. However, when confronted with a rich man trying to stay rich by pointing this particular nugget of wisdom out to me, I can become a little more direct in the matter. What a load of. Well, you insert your own suitable words here. Because also here, it doesn't really pay to get angry, and quite frankly, I can't be bothered either. The actual point about the troposphere is much too awesome. We know all the physics happening, we can explain, but we can't describe the correlations well enough to predict the weather. It's pure chaos in both the urban and the mathematical sense. The sphere of changes indeed. Above it, we find the sphere of layers, the stratosphere. What a name. The layers within the sphere refer to the temperature development upwards. There are volumes of rather constant temperature gradients which from below look like two-dimensional layers. It's an historical thing that also gave us the ozone layer. The stratosphere extends to 50 kilometers altitude everywhere on Earth. There another temperature gradient inversion takes place. We will get back to that one a little later. The stratosphere then, for all its ordered volumes within the volume, is still a place of, quote, intense interactions among radiative, dynamical and chemical processes, in which the horizontal mixing of gaseous components proceeds much more rapidly than in vertical mixing, end quote. That's from Wikipedia too. In other words, the stratosphere is just as complex as the rest of the atmosphere, no matter whether the air is a little thinner or not and whether the energy flows mostly sideways or not. Let's dive into this a bit more. An interesting feature of stratospheric air movement is what's called the quasi-biennial oscillations, or QBO, which happens in the tropics. It's air movement that's driven by the sort of pressure waves you already talked about, even though the ones who are relevant here are generated in a multitude of ways down below in the troposphere. The QBO then induces secondary circulation that is important for the global stratospheric transport of things such as ozone or water vapor. Another thing are sudden stratospheric warmings caused by the absorption of those planetary waves I talked about, which can often be observed in the northern hemispheric winter. Hold on now. Ozone. I said ozone. What's ozone? I mean, we've all heard about it, but what is it? It's an invisible but poisonous gas. Its molecules consist of 3 oxygen atoms connected to each other at an angle. Its color is rather pale, but it's soluble in water and condenses to a deep blue liquid at minus 112 degrees Celsius. By the way, the Greek ozein means smell. You know that smell too. You'll find it in rooms with printers or other electrical equipment unless you air those rooms out very well. Electric cars smell like that too, in the cabin when they've stood for a while. Some people like that smell, some don't. It's ozone. It's poisonous. A lot of the relevant ozone reactions need a lot of energy quickly. Thus it absorbs high energy UV light and does a few things with it. Yes, there's some visible light in there too. Now, if you want to go look up the actual chemical reactions, do so, but you don't need to. The point is this: ozone gets created and destroyed slowly, but with the help of reaction participants that are abundant, that is, single oxygen atoms and O2. UV light, which is just as abundant, helps destroy ozone again. There's an equilibrium which reduces the amount of UV light reaching Earth, and that's a good thing, unless, of course, we mess with it. See, in the 1960s, they thought they could explain everything with the help of what's called Chapman's equations, after Sidney Chapman. If you've searched for the chemical reactions just now, you probably found these. Observations, however, showed much faster ozone destruction than what those chemical equations predicted. So, it was remembered that scientists had already shown a decade before that hydroxide and hydrogen peroxide could influence the amount of ozone in the air. Scientists then followed that idea a little more and found out that many so-called radicals, of which these two are species, could help accelerate the destruction of ozone. The connected reactions were and are very fast, yet, thankfully, there aren't all that many of these radicals in the air, comparatively. By the way, if you can't remember your school chemistry, don't worry. Radicals are simply atoms and molecules which are about as ready to react with something else as it gets. You know where this goes now. Nitric oxide, chlorine and things like that are all such radicals, which do have a catalytic effect on their respective ozone destruction reactions. That is, they come away unharmed and can continue doing damage. What's more, we put a few of these gases in the air. We still do it, although not quite as much as before. We call them CFC gases. It's worth noting that the CFC gases don't climb too high into the atmosphere, most certainly not to the top of the stratosphere where the ozone is made. Ozone sinks, though, so there is that. And once it sinks, it'll get into stormy airs, literally. Remember that idea about turbulent motions, distributing everything that's in the turbulence smoothly over the whole volume? Well, what I want to talk about happens in the lower stratosphere and upper troposphere, especially in the polar regions. It isn't necessarily turbulence, but has the same effect: polar vortices. The polar vortex goes by many names: polar cyclone, arctic cyclone, subpolar cyclone. Okay, these are basically similar words thrown together in different ways. But whatever you want to call them, these are some of the mightiest storms on Earth. They're located near the poles of the Earth and usually span around 1,000 to 2,000 kilometers in diameter, while transcending our layering of the atmosphere, reaching from say 5 kilometers altitude up to perhaps 20 kilometers. The reason? The Coriolis force, though indirectly and connected to the Rossby waves we talked about. Rossby waves may dissipate their energy into these polar vortices. To boot, polar vortices are as deep a rabbit hole as they come, knowledge-wise. To start with the Wikipedia article I link to in the description and descend into a wonderland of stratosphere and troposphere physics. It's awesome. If you don't want to do that and you happen to be from, I don't know, Florida in the United States, then just realize why you experience cold spells when they shouldn't happen. It's a hurricane above your head or slightly off from above your head, with wind speeds up to 4 times more than what you call a hurricane. They call that hurricane the circumpolar whirl. Not kidding, that's a name I forgot a minute ago. What does that mean for ozone? We may and do measure lower ozone densities during times of the polar vortex. That doesn't mean that there's less of it when the polar vortex is on, but it's stretched out and less of a dense layer the way we imagine it. Finally, we come to what's called polar stratospheric clouds. You may know them as mother-of-pearl clouds due to their iridescent and frankly wonderful colors. Know that when you see them, they'll be between 15 to 20 kilometers above you. Their exact altitude depends on the size of the ice crystals they consist of. The smaller these are, the higher up the clouds will be. Truth is, we don't know all that much about them for certain, despite a rather determined Wikipedia article. Again, as with all clouds, the devil lies in the nucleation, that is, the way the icy particles that make up the cloud come to be. The stratosphere is dry, so something needs to be there in order for what little water there is to crystallize onto that something. We have some inklings about what that something could be. We know, for example, a couple of the chemical reactions the clouds take part in. They remove nitric acids in the air and have an effect on the nitrogen and chlorine cycles in such a way that they contribute to the destruction of the ozone layer. So yeah, I guess. They're beautiful though, because they receive sunlight from below the horizon and scatter it towards us. There are a few elements to the colors of the mother-of-pearl clouds, but mostly those colors are connected to the form of the crystals. Read more on them if you want, it's well worth the time. Here, I'll take you higher up with me now. Let's cross the 50 kilometers altitude line into the Mesosphere. The Mesosphere is the sphere in the middle, pretty much literally according to the word itself. It reaches up to 90 kilometers altitude. Its most distinguishing feature is that we don't really know much about it. Well, we do have quite a bit of apparent trivia, but nothing on any deeper level. We can't reach it anymore with balloons or any other flying apparatus to make direct measurements. What about satellites, you ask? The lowest somewhat possible orbits for those start at, 150 kilometers or something like that. In other words, satellites are further away from the Mesosphere than we are. Yes, they are rockets, and they do qualify as flying apparatuses, but they come with their own problems. They slice through the atmosphere at speeds which make the air flow around the instruments on them so complex that, well, we can still measure stuff and conclude things, but again, only at the apparent trivia level. Particles, for example, can be detected and even counted, but only in relation to themselves. Normalized is a term physicists use. Basically, all uncontested rocket-borne measurements in the Mesosphere are normalized. So this is cutting-edge research, really. And how do we conduct it? How do we find info at all about this layer of the Earth's atmosphere? We'll get back to the rockets in a second, but first think of antennas or lasers. That's easier. We put them on the ground and point them upwards. Remember how I told you about ground-based telescopes in the piece on the observable universe? They're sitting on mountaintops because the atmosphere doesn't disturb their observations as much there, since there's less atmosphere above them. What if those disturbances were exactly what we are interested in? The disturbances are often connected to things like water densities or electron gradients. For the first one, you can gear a laser such that it reacts with whatever substance you want it to react to, by giving it the right frequency/wavelength. That would be 1064 nanometers for water molecules, for example. For the second one, you can build radars which react to changes in the electricity in the air. The great thing about these lasers and radars is that they just sit there and measure. They can do so for years and years and years. Their data is not that difficult to process either, such that a researcher can sit at home while making measurements at a completely different place on Earth and getting decent results more or less in real time. Check out the Marcy radar in the north of Norway to see what that would look like. I'm not sure about your background and confidence, but note that we talk about an altitude resolution of, well, I don't remember exactly now. I just remember that it isn't necessarily all that good, all things considered. So what about rockets then? You can put instruments in these, launch the rockets, and then use either experience or supercomputers to deduce anything from the measurements. It's quite tricky sometimes, since those rockets are fast enough to beat sound to the punch, as it were. The supersonic aerodynamics around exposed instruments is not for the faint of heart. Still, one can get rather beautifully tight and nice resolutions in the data, if only for a fraction of a quarter of an hour, to put it like that. So, no, it's not ideal. It's either supersonic aerodynamics or low resolution in the data, and in both cases the observations are rather limited geographically. Expanding into the whole atmosphere, this means that we can't really be sure of anything unless it hits us straight in the face. I mean, I guess you could get a meteorite falling onto you while looking up, but the probability for that is lower than, I don't know, for a particular passenger plane of your choice spontaneously assembling at a predetermined place in New York City's Central Park, something like that. Anyway, let's see what we do know, shall we? We know, for example, that these atmospheric pressure waves I've talked about propagate vertically too. At least a substantial amount of them do. I've already mentioned it more or less between the lines. The problem with that propagation is that the air grows thinner and thinner while going upwards, while the energy in the waves doesn't decrease quite as fast. In other words, at one point the environment will no longer be able to hold that energy and the wave will break. Imagine an ocean wave closing in on a beach. The actual physical processes are different, of course, but the underlying idea is the same. Close to the beach, the environment will no longer be able to hold the energy of the incoming ocean wave. The wave breaks, and we get these fine little tunnels, vortices as we call them, in fluid dynamics, through which surfers can, well, surf. Wave breaking happens to a substantial amount of atmospheric pressure waves in the mesosphere. Especially at the top of the mesosphere, between 80 and 90 kilometers altitude, this has interesting consequences. Remember how I said that everything within turbulence gets spread out evenly, more or less, like in the smog over a town within the planetary boundary layer, or within ozone in polar vortices? Of course you do. But yeah, the same thing happens here. The layers are from a couple of 100 meters to maybe 2 to 3 kilometers thick. What? Oh, yes, you're right. Readjusting air molecules probably isn't quite that exciting. There's no smog or ozone either at these altitudes, so what's being distributed evenly here? Enter shooting stars, literally. It's rocks creating the shooting stars when they enter the Earth's atmosphere and become gas. That's what you see when you look up. Stone becomes gas, creating shooting stars or meteors as they're also called. Both names are given to the light phenomenon, not the stone itself. Those are called meteoroids for as long as they fly through space. They're like asteroids, but smaller, very much so. We're talking small grains, no, not pebbles, but grains, and up to 1 meter wide stones of death. Most of them are just fragments of asteroids or of comets. Sometimes they are leftovers of much, and I mean much larger collisions on other heavenly objects, such as the Moon or even Mars. Up to 100 tons of stone can come into the Earth's atmosphere in this way. Stones become gas. Perhaps I shouldn't brush over this, because I mean it. They don't bother with melting or anything like that. They get so hot that single molecules of stone, I know, bear with me please, are released straight into the air. The process is called ablation and happens very quickly at very high, actually white-hot temperatures. That means that during a meteor event there is stone gas in the air. Nature doesn't want that, such that the stone molecules find each other to build small nanometer-sized particles. When there's turbulence at this altitude, then it is this sort of particle which gets spread out evenly into a meteoric cloud almost. In addition, it can get cold, like really cold, minus 140 degrees Celsius that is. And that's also due to atmospheric pressure waves from below, albeit in a different way. You're not gonna like it, but well, let's start this way. Have you ever wondered why maths, especially complex maths, even exist? One part of the answer is about how maths makes us know things which we otherwise wouldn't. Check out a piece called Imagination and Mathematics for a deeper discussion of this. But let me ask you another question here. How does it look like to use maths in order to gain deeper understanding, quote unquote? How does it look in practical terms? Imagine a pressure wave. Well, at least as well as you can, moving through the atmosphere until the air gets so thin that it can't hold the pressure wave's energy anymore. From all that you know about physics and your own experience at beaches and so forth, you'd expect what I described just a minute ago, which is wave breaking and vortices and, in a word, turbulence. Strangely, it doesn't always happen like that. The energy released from the breaking pressure wave may be used by nature to drive a wind, a global wind which flows from one polar mesosphere region to another. But wait, how is that possible? Aren't there such waves on the opposite side of Earth too, pushing back, as it were? There are, but it turns out that the balance favors a wind direction from summer to winter pole, that is, that this gigantic mesosphere wind shifts direction twice every year. That in itself is quite the thing to ponder, and we know it only due to doing the maths. But it also explains why it gets so cold. It does so in the summer months, when pressure wave driving, as it is called, creates a humongous volume of low pressure, and with that of low temperature, at the top of the mesosphere. And that leads to something utterly weird and beautiful, noctilucent clouds. Imagine it all coming together. Turbulence, meteoric dust, and a volume of such low temperature that whatever little water there is in the air at that altitude will crystallize onto the stone particles. Since everything is spread out evenly but also focused in on these layers, we can see the wonderful clouds in the twilight towards the polar regions during the summer. I've got a link in the overlay cards and a description for a little video on how they look, seen from where they aren't. Remember what I said about the polar stratospheric clouds and the geometry of Earth. It's valid for noctilucent clouds, only more so because polar summers bear with them the midnight sun. There's no night or even twilight there during summer. I've done scientific research on them for 9 years and had to move south before I ever saw them for the first time. Well, anyway, they're clouds, and as for all clouds, the biggest problem is the growth of the single particles, in this case crystals building up on meteoric dust. They grow, and following old Archimedes' ideas, they sink as they do. In fact, they can grow to sizes of several tens of nanometers, and when they do that, they sink out of the cold volume and the ice melts again such that we lose track of them. Almost, at least. That radar in northern Norway I've mentioned can follow them for a while still. For all that, we don't really know. We think that they sink far enough to be able to contribute to the creation of mother-of-pearl clouds and the destruction of ozone. It would make sense too, but we don't know. It's a similar situation to the Epic Oort cloud of astrophysics. Yes, there's a link there in the overlay cards and the description. Well, no, I've put 5 videos into the overlay cards already. Check out a link in the description to a video on comets, science, and dads. You know, when I used to work on these things and people asked me about them, there was always this, okay, but why do you do it really connected to it? For a while I told people that basic research about nature was what led to quantum physics, to our understanding of the universe and things like that. It never seemed to hit the right nerve, not even with my mom sometimes, I recall. Yet it's not difficult to understand why we want to find out about the mesosphere. Perhaps you have even caught enough of what I have told you to not need my help now in finding out the why of it. 100 tons of stone may enter the Earth's atmosphere every day. We know part of what happens with all that material, but don't know the whole story. We do know, however, that whatever is part of the atmosphere has an influence on the energy budget, on how the energy flows and how it affects us where we live. Just because we put a label on these different layers doesn't mean that the atmosphere isn't one whole thing. Actually, we need to include the Earth itself in that system too. All of it, land masses, oceans, air, all of it interacts in a way that is fundamentally important to us, since we live on it and in it. We're part of it too, is what I'm saying. So, yes, we have to know what happens in the Mesosphere too. But yes, I also understand that it's not as sexy a field to do research or even have the slightest interest in. Not compared to, say, Northern Lights. These happen in what's called the Thermosphere, the almost topmost layer of the Earth's atmosphere. In fact, for all intents and purposes, it is the topmost layer, since the so-called Exosphere, which is technically the outermost layer of Earth, derives its name from the very fact that there isn't enough air in it to really be of any interest. Well, that's wrong as far as absolute statements go, but it is true enough for the purposes of this piece. In the description, I'll have the Wikipedia article for you. It's interesting and rather short. The Exosphere is quite literally out there. So, the Thermosphere. What's the Thermosphere? It's the thing most people call the ionosphere, since it's where ionization really, and I mean really, enters the equation. Well, all of the equations we can use to calculate stuff. The thermosphere draws its name from the Greek word thermos, which means heat. That heat comes from solar radiation, which to a great degree is absorbed already here. In fact, temperatures can rise to 2,500 degrees Celsius, although one has to be a little facetious in saying that. The word temperature doesn't quite have the same meaning up there as compared to down here. Think about it. When something feels warm to you, then that is a direct consequence of atoms and molecules banging into you. You feel their impact on the whole. Up there just aren't many atoms and molecules to bang into you, so you'd still freeze to death, unless you're directly exposed to solar radiation. Then you'd fry to death, since the energy your body would absorb couldn't be transferred to anything around you in order to cool you down. For the same reason, there's no sound up there, at least no sound you can hear. Take that, Star Wars. It's all about incitant energy by the sun. The way scientists describe this in their papers is by calling it diurnal heating. Twice per day, that's what this means. There are two parts to this rhythm, and they follow day and night. As you probably know, such diurnal differences in incitant energy, quote-unquote, happen down below as well. The weather, that is, the air movements and temperature and everything changes from day to night and back to day. Just imagine how things must be up there, in the first line of defense, so to speak, with only a few atoms and molecules to take that first onslaught of energy from the sun. No wonder we find electrified gas there, so-called plasma. Yes, that's what that word means when they talk about TVs too. Electrified gas. There's so much energy in it that even the molecules can't hold on to all their electrons. The plasma moves around too. That air movement is called atmospheric tides. They're awesome in their own right and recommended reading for those who want to delve deeper into this particular subject. Then there's this sentence on Wikipedia, and I quote, "The thermosphere is uninhabited with the exception of the International Space Station, which orbits the Earth within the middle of the thermosphere between 408 and 410 kilometers. Never ever edit this out, please. Apropos astronauts. They're the only people who have ever seen aurora from above, and on both sides of the polar regions. See, when physicists talk about solar radiation, then they don't just think of electromagnetic waves, that is, light in its different forms. There is also a more or less constant particle stream emanating from our star, and that particle stream carries energy too, a lot of it. In fact, it carries so much energy with it that it can in principle obliterate whole planetary atmospheres. That's what happened to Mars as far as we know. Mars is a desert planet now, but it used to have an atmosphere then. That atmosphere got blown into space by what's called the solar wind. That's the particle stream I'm talking about. Earth is closer to the source of that stream than Mars. Why do we still have an atmosphere? Because of our magnetic field. I've talked to you about magnetic fields before. Find links to videos called Magnetars and Curious Aurora below. They're awesome stuff. Without Earth's magnetic field, we'd be dead. Just to say that straight up. The solar wind, fortunately, consists of electrically charged particles, electrons and protons. Such particles on the move have a magnetic field which can be interacted with and deflected by other magnetic fields. Thus we are alive. To be sure, there's a lot more to it, and if you're interested, then use the link to the Wikipedia article about space weather as a starting point, and dive into the references at the bottom of the article. It's about as awesome as it gets, and just as chaotic a system as the weather in the troposphere. Here, the point is, if that magnetic field has an opposite polarity to the Earth's, then the magnetic fields can basically melt together and some of the solar wind can enter the Earth's atmosphere. Once the particles are inside the Earth's atmosphere, they follow the field lines of Earth's magnetic field. Some of the particles are channeled directly towards the polar regions where they collide with the molecules and atoms in the thermosphere. These collisions can be visible to us, especially when they happen in front of a dark sky, and often enough at the same time and the same place. These are quantum physics collisions, that is, they lead to atoms and molecules jumping around in their different quantum states, as they're called. When the particle loses energy, it does so in the form of light, which we may see. When the particles are directly channeled towards the polar sky, then that happens at daytime, which means for most of the year the resulting light phenomenon is only visible by instrumentation. During the polar night, however, and way up north, say at Longyearbyen on Svalbard for example, you can see what's called daytime aurora. The touristy, flashy northern lights, however, happen on the night side of the globe, and one can ask the question of how solar wind particles get there. Good question, with a weird answer. And you know what? I'll let that answer be for the nonce, since it is utterly and thoroughly connected to something called magnetic recombination. That right there is worth a couple of videos even, so we'll look forward to them, right? I mentioned earlier that the ionosphere isn't really just up there, but everywhere as it were. What did I mean by that? Well, there are electrons and ions in the whole atmosphere, even around you where you are now. There are smooth transitions to more and more ionization upwards, unless of course a northern lights event or any other sort of electron precipitation happens. In other words, we just live in it too. Don't believe me? Let's talk sprites then, shall we? No, not the natural spirits. The atmospheric electric discharges. You haven't heard of them? Well, here's their story. Whenever there's a storm cloud, then there's a good chance for significant separation of electrically charged particles inside that cloud. Electrons will amass towards the lower edge of the cloud, while positively charged ions drift upwards. In fact, many ions will leave the cloud and enter the ionosphere, where they redistribute over the whole globe and descend again wherever there's no storm cloud to keep them from doing just that. As they reach the ground, they travel back to the original storm cloud. If you're wondering, there's pretty much always a storm cloud somewhere, so this global electric circuit is there constantly. If you've ever built your own electric circuit, you know that you can send too much current through it. With respect to pressure waves, I call that having too much energy for the environment. Pressure waves break when it happens. Your electric circuit burns through some resistor or transistor or some other component, while the global electric circuit produces atmospheric discharges. Lightning, in short. Lightning is awesome in every sense of the word. And that backstory makes it easier for me to tell you that these sorts of discharges don't just need to happen between a cloud and the ground. Due to the thinner air, there is even more reason to assume that the energy in the global electric circuit can lead to discharges above the clouds. And so it does. They're called transient luminous events, and they're everything a nerd like me would want in his physics. They have funny names. There are sprites. Stratospheric/mesospheric perturbations resulting from intense thunderstorm electrification. There are elves too, emissions of light and very low frequency perturbations due to electromagnetic pulse sources. There are gnomes, trolls and whatnot. On top of that, they're just magnificent. Sprites can have vertical extensions of up to 60 kilometers. Elves can grow to several hundreds of kilometers in size, and all within a few or less even than a millisecond. Blink and they're gone. Like, sprites, elves, gnomes, trolls, and the ever-present whatnot. Awesome. I mention these things because they transcend every sort of layering we try to put on the Earth's atmosphere. I made a little bit of a fuss about us categorizing galaxies in that piece I mentioned called The Center of the Universe. Yet make no mistake, categories like models help us understand what we see. But also, like models, we need to make sure we understand the limits of the categories. One part of history that is often forgotten is that scientists thought for a long time That those layers were just that, actual layers. No energy transport up and down, apart from solar radiation downwards, of course. Yet, this has never been true, not by far. Just ponder for a second what we've been talking about in this piece. Yes, the troposphere is defined as the volume where infrared radiation is the dominant force, but apart from that? Polar vortices in strato and troposphere, northern lights in exo and thermosphere, meteorites which slice through all of the upper atmosphere. Even ozone is found in both stratus and troposphere. Different types of clouds too. Now, I can't leave just like that and not mention that the vertical energy transport is not necessarily investigated well. It isn't at all. Whether meteoric particles, for example, take part in building these wonderful mother-of-pearl clouds? It's possible, it's likely even perhaps, but we don't know. Speaking of meteorites, the Earth's middle atmosphere, that is, the Mesosphere and its wonderfully weird physics, is what became my field of expertise. And still, I'm rather sure I've made factual mistakes in this piece too. I always do. We always do. And I'd like to hear from you about them too. A comment and a link to something which helps all of us, including me, learn. If you have the opportunity though, step outside, take a deep breath and ponder for a while what this means for you. Then set those thumbs up under the video, share it with your friends and subscribe before you comment. I mean, how does it all affect us? And we, it. Let's talk Earth together.